Okay, right now I'm starting taping. This is pretty much for Eduardo Ceperuelo, who is a professor at Rio de Janeiro, and he is probably thinking about joining us. But the idea of veiling, if you have a oh, by the way, can you guys see my screen? Probably not yet, huh? Yeah, so typical photosphere of a star, even, wait a second. Just a second. Got frozen here. There you go. There you go. Okay, so Vikas, so any given star with a photosphere that has molecules or atoms or ions, when light from the interior passes through this cold atmosphere, it's the atmosphere will produce these signatures, and the signatures we call absorption lines. Um, so in a premium sequence star, in addition to them having photosphere, they also might have some emission that comes from different regions. And so if you add these two features, one is a series of absorption lines with some external emission continuum. So if you add those two, um, the final result, once you normalize, is a veiled spectra, which which is one that has the same dispersion, but the absorption line seems to be a little bit shallower than they should be. So what we do basically, or what we did in the first part of this exercise, was to determine which external emission should be added to a template, which is we take as template a photosphere of a star that's not active at all, and then we add some variable amount of emission and see which one provides the best fit to our series of absorption lines, and we call that veiling. That's right. And the chi-square analysis, I mean, there are several ways of approaching. The one that I like the best is a kind of an independent um, from human biases in a way, is just to go with a range of possible veiling factors, all in steps of 0.05, which is very small, and then see which one provides the best fit to a small range of the stellar spectra. And usually this small range is 10 angstroms, so this is not that big at all. And in the routine we developed, we try to we have two specific modes. One is completely automatic, and what it does, it takes chunks of 10 angstroms and do this chi-square analysis, find the veiling, and if the chi-square is less than 5%, it saves that as a possible value for that spectral range. But sometimes you still have some bugs, some bug in not in the code itself, but in the absorption line. Sometimes in that specific region, you have some telluric molecules from our atmosphere that is affecting your result, and sometimes the results are not good. So what we are going to do later, when we are more comfortable with what we got, is to eliminate all these possible junks out of the veiling determination, and then use the scattering we have as a way to assess our error bar in specific regions and see how that error bar propagates when we measure fluxes down the line. Yes, yes. Not only Earth atmosphere, but also when you break the, the premium sequence spectra in chunks of 10 angstroms, sometimes you might get some emission line from the territory in that range. And then when you have some spike emission lines, which is not typical of this type of stars, but is, I mean, it's typical of premium sequence stars, but not of templates quiet stars like the sun. The sun doesn't have emission lines. So, but when the premium sequence star in the region we are studying presents some emission spike, it's going to affect our results. So we have to be able to screen all of those bad emissions out of our determination. But this we can do down the line. So I was talking to Philip when we went to measure the emission flux of helium line. We found that the match was not perfect. Let me see if I can show that to you. So we have a routine that is this one. And then what this routine does, it compiles. After you compile, when you run it, you can run for instance, this one. It show up your helium line. So what we want to do is to measure the emission flux, to how many photons are there above continuum. So to do that, we have to normalize first. That's what I'm doing here. And then normalize also the templates. This wing here in absorption is in fact the big wing of sodium line. So this is real. So the continuum is pretty much up here. So and then it shows for a small region of 5860, so 10 angstroms, right? So we have some absorption lines here in white. The white is a priming sequence, and in red is a T-torr. So when we measure flux, this emission flux in helium, the code that I put up there allows you to make small changes. For instance, here I'm reducing manually the veiling to try to get a better determination, but it's not it. So it seems that here it shows almost a perfect fit, at least for these three lines. So the veiling for this particular record is 0.8. So the one that came out of the automatic pipeline was 0.7. Let me see if that was the case. Start all over. So we do continue. Oh, that was bad. Do again. Better. And we do the template. So the automatic pipeline calculated was 0.6. So if I think this is not a good one, I could say, well, this is better, 0.8. And that's what's going to go to the process of flux calculating. So click left of the window to save any. Did, and now we have the ability of measuring. So what is complaining here? Oh, because I didn't compile line flux. Doesn't go to line flux. So and then once it's kind of a fudge the veiling, the automatic pipe routines calculated, it allows you to measure the flux emission, which we want to do in all 92 data sets, so we can do further analysis and see how this flux emission change over time. And this is a scientific result. So that's what we want to do. We want to know how the emission flux change over long period, over short period, and over consecutive nights. And I will show you we have these consecutive nights in our data set. So let me do it again with this reading one. So we measure 1, 2, 3, maybe 4. 1, 2, 3, maybe 4. Let's say we are happy with it. Now, so what's being shown here is the helium line in emission. So this green line indicates the line center. This is where the center of line theoretically or in laboratory is measured. 5875.621. And then you see the peak of line is exactly at that point. So I'm not choosing this point here because it's the peak. It is the standard laboratory value of it. So first of all, it says that our radial velocity correction is done okay. So we are happy with that. Second, you can see by looking at this line, there are two components. One is a kind of a broad and asymmetric. If you think about a Gaussian, so this is a broad Gaussian here. And there is also a narrow emission, but as far as I remember, we all thought this narrow emission was symmetric. As you can see here, it's not. It is not symmetric at all. And when we work on this paper, with data we observe, and there was not a lot of data, but it had the advantage of having consecutive nights on it. We didn't do radial velocity corrections like we did here. We were not that careful. We had a short time to complete the work, and I was in the process of moving, so it was all confusing. Um, so we didn't spend a lot of time doing the basics, which we should have done, but I didn't. And then I thought this narrow emission was pretty much symmetric, and here I can see it's not. So you have the red wing is kind of opening up, like the broad component. Also, the red wing is opening up. So later, when we all had time, what we should do is to try to decompose this profile into profiles. See which Gaussian can be fit here, which Gaussian can be fit here, and if this red asymmetric component can be measured. And this is something we have to devote some time to look with more detail, which I can do now. So, but then once we go to this routine, we mark two points, and then it measured the line flux 3.595, and then we save that. And then the routine, what it does, take this flux emission and put in a file, so that we can later down the line we can analyze the emission of every single profile. Okay. What I would like to do, and I know now you guys, Philip is starting class now, Shaunak in 2 weeks or so, and I in September I start classes, so my life gets all confused again. It's already confused, but it's going to be more confused later. But what I would like to do is to every week to read a paper that is pretty much meeting our interests right now, so that I could get you guys a little bit more familiar with the research itself and what's going on with these stars in the field. So if that would be the case, and just to set out time, I will look at my schedule in the fall, and I set a few options, probably make a monkey survey or so. When would be a good time for us to get together in the evening every week? And then I would probably go over some of the basic issues, 30 minutes or 40 minutes, and then we would discuss what results we have over the week. We had the chance to do some calculation or something, and we could probably set a time this coming week to have that done for the first time. That would be great. Yeah. Okay. Okay. Hey Lee, how are you doing? Well, not well. The idea is I'm going to open papers. Probably the one that I should start first is the one we did with TW Hydra in 2001, 2002. I don't think there is anything much different going on in the literature from what we did. This paper received some citation. It still receives citation. So I would be easier for me to start there, and then we can spread out from there. But I would probably take 30 minutes and highlight aspects of the paper that are of interest to us now, and what we had as a result in the past, and what we can accomplish now with the data we have. Um, and that would take probably 30 or 45 minutes, and then we would open to discussions. And then after that, in the second aspect, I would like both Philip and Shaunak, or any other student we might have in the high school, I would like you guys to show um, presentation, to do a presentation of what you could what you could develop in in a week or so. If not was done, that's okay. But if something was done, what was done, and then he would do a little presentation. We had established some landmarks to be achieved by now, right? By August, first week of August. So we fell short of it because we've had a lot of pitfalls, but I think we can try to reassess this schedule for, let's say, November or so, and see if we can in November get together again and see if we were able to meet our our deadlines. But we should try to work with deadlines and try to meet them. That's the best we can. Best we can. So in particular, the Sphere Network, it's a network of high school students who are doing research, like open-ended research, like the one we are doing now, and that is managed by Professor Raja of UC Santa Cruz. We'll have a presentation on August, I think is Tuesday, the week your class starts. So I think Shaunak can't be there, and neither Philip. So I think both of you can't participate. But I will tape it, so you guys can, later on can watch it. I think it's at 9 o'clock. That's my understanding. 9 a.m. on Tuesday. Yeah. No, this is an online. This is an online conference. I don't think it's an open link. I think they give link to one of the persons who are managing students. I will ask Raja if I can pass that link over to you guys, and then if Lee could attend, that would be good. At least, or Rick could attend, that would be good too. But I have to ask him. He sends a link. He sent links to all the PIs that are managing high school students. Yeah. Who's gonna give talks? Um, uh, as far the sphere presentation that I attended last time was, I mean, Raja did an opening, and then there was several high school students from different groups doing presentation on what they are achieving. And the presentation was very formal, but took 15 minutes or less for them to do presentation. It would come with a PowerPoint presentation, the data they are trying to work on, and results. And the area was all kind of areas. So we had marine biology, we had meteorology, there was one or two astronomy fields, and yeah, it's pretty much open. It's for high school research in STEM areas. So I would like, once both Shaunak and Philip are ready for, to do a presentation and have some of the work done. At least this can be used in future CVs when it's good for them. Yeah, yeah, yeah. But if not, I would tape. So I will tape, and I will send the link to you all. It takes 1 hour. It's 1 hour. Yeah, it's 1 hour, an hour and a half, and it's a brief presentation of Raja. Say, hey, is everybody okay? And then he start calling the students who are supposed to do presentation. So their PI come in and then present the students, tell what they are doing, and then voila, the students start uh, going and presenting. But it's formal because it has PowerPoint, it has animations. If there are any, you guys could do animations with Picamission as they vary over time. Every 2 months, once every 2 months. Maybe. I mean, we have to put in his schedule. I mean, first we have to finalize something, and you guys have to be comfortable to express what you guys have found, and have some idea of where to insert what you found in the context of research that's going on right now in this field. So that's why in my side, I would like to start giving talks on papers so that you guys become familiar with what's going on. And I know you don't have time. I mean, your priority is to get good grades in school and be also in math and computer and all of that. That's your priority now. So but you can learn what's going on just by talking and by being in a relaxed environment, learning science. But more so, you're going to learn a lot when you have the data and you start thinking about the data, playing with it, analyzing, and doing correlations and finding trends, and that's what we wanna be at, is when you start to finding trends. Yes, 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 yes. Oh, we could we could yes. In fact, we could kind of wait a second. Let me see. Wait a second. Yes, yes. Wait a second. Oh, okay, these numbers are the Julian date of observations minus the first one. So see how interesting the data is. See these numbers here? 754. So these are two observations done in the same night. This is the next night, two observations next night, and then the following night, two observations, and then the following night. So we have basically one night, two, three, four, five, six, and then jump two, right? Probably bad weather. Seven, uh, eight, nine, 10, 11, and then goes 3 days later. So it's so if you go from here, so this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So from 2 to 22, so these are almost consecutive nights. So we could, because I was playing with it before you guys came in, we could do it again. Restore. Oh, this is waiting. Um, so I wonder if we could. We could do a simple program um, like this. T. Julian days for record and 2, 22. Do begin. Restore. Use CW, TW, Hydra. Now I have to know where I put my data. Just a second. Celsius Mac, Macintosh. Oh, there you go. TW, Hydra. Oh, that's the one. TW, Hydra. Yeah. TW, Hydra. Right. And then TW, HYA. And then string compress. Record number. Save. Okay, so I'm going to read the profile. I'm going to read the profile. And plot them. So I'm reading the profile. I'm doing a routine just to read the spectra and plot WT S WT ST. No, I'm gonna cut first. Cut WT ST 58605890 and put in WS SS E SCS equal SCS divided by its mean, just to do a simple normalization. What Lee? Ampersand is when you are inside the loop and work in the command line, is telling you that there is more command coming in, and then you put the ampersand for that. It's a new line of command, and I'm putting just as a string because this is disposable. I just wanna see. Lee made a suggestion to see what's going on in the profile, and I just wanna quickly check that. Yes, yes. I start right here for rec. In fact, I could take all of that out. Yeah, so I really don't need that. Um, I know, and it's different in different languages. I'm pretty sure Python has something similar. And then we're gonna plot WSSS. Um, put a range and plot. Let's put that line for the center line, 5875.621, 5875.621, 09. So we have that. Color is equal, I don't know, 230. What else? And wait a few seconds, and 4. It's too slow. Stop that. So these were profiles observed over those consecutive nights. You say asymmetric, yeah. Um, it's around 4.5 days, and that's why these consecutive nights are interesting because it goes over 2 of that. That's right. That's right. Well, that's what we want to. I mean, when the boys are done calculating the flux, then we can ascertain that. We can verify if there is something periodical or not. So I could also plot out zero. Right. I'm sorry. Say it again, Ogden. Oh, go ahead, Lee. Yes. Right. 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 So once all this data has been placed somewhere, um, Philip and Shauna can go there and pretty much use Python routines to do analysis. Right. Or IDL, yeah. Yeah. Well, but the people outside doesn't care for that. They want to see data. They want to see conclusions. I mean, what you guys found, no matter which platform you use. Yeah. Yeah. Right. 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 Yeah, they expect that. This is pretty much expected. So, so where this leave us? I would imagine now is a measure of using the dating. I don't know, Shaunak, where what would you like to do? I mean, where are you now? I know you want to work more with Python, but would you be able to make use of the ideal routines that we are exchanging now? If you do, I would send you so you could try to install at least get the data in your machine, and then you can work um, with Python to get that data analyzed somehow. Okay. Okay. So I'm gonna send the routines that do the line flux measurements, this Helium 15875 and the Line Flux Pro. I'm gonna send them to you and to everyone, by the way. So the only thing you need to do is to go in this routine and put the address to where the files are. Pretty much that's it. And the files must be in saved format. But you can change the routines and read the file in FITS format, but you have to make the change there by you. And again, I would be available to, if you want to work with me, I would be available to guide you through using the Zoom platform. Mm? Same with uh, any any other person, right? Eduardo, if Eduardo would like to do that, that would be fine too. Yeah. Eduardo is he works with me in Brazil, and he is a professor in a in a. It looks like a community college. It's a different system. Is maintained not by the state, but is maintained by federal funds. And he does have undergraduate students, and the system there it has a little bit more contact with the high school, by the way. Uh, so he thinks he can get a couple of students, and we published paper before in the GQ Lupi. We have a good data set for GQ Lupi. I look at Theros data. There's not a lot of a GQ Lupi data in there. But that could get him motivated to get his old routines ready to go and just initiate it like I did. Um, I don't know. I don't know how Brazil is standing now with Theros. The latest I heard from Natalie said that Brazil is out of a ISO consortium. And if that is true, he doesn't have access to that anymore. So I don't know. That would be bad. So if he does have access to observations, maybe if we can get some milk out of this cow, he could perhaps submit some proposal, and then we would get some fresh data. All right. So then, Shaunak, I'm gonna mail the routines. See if you can work on them. I will be off and on computer today and tonight. So if you wanna kind of reconnect tonight, that would be great. Philip, I know everything is working for him, right, Philip? Okay. Then, if that is true, perhaps we could try to discuss again. No, let's put it for Wednesday. Wednesday or sometime this week, we get together, and then what you could do is to get some little routine that would read all this flux measured and put in a format with the Julian date or with veiling, and then we could start correct connecting trends. For instance, does your line flux correlates with veiling or not? Is there a correlation with it or not? Veiling is directly related to accretion rate. So if your line flux correlates with accretion rate, this is a good indicator, right? So then certainly this line is being pumped by some external factor. Um, and then we could look at different line fluxes or different lines in order to determine how these different lines correlate with one another. So is there a common mechanism pumping them out, or it's just one line is more sensitive than others? It's good. I mean, the line flux. When you say amplitude, we are. I mean, yes, yeah. That's something the boys have to find. I mean, I would expect to be, but yeah, because I think that's what we found in 2001. There was a correlation between the line flux and accretion. Yes, that's their goal. Yeah. Oh, it's a lot of pressure. Okay, you guys are in charge of next week presentation. I think it's good. I think it's good. And then they could compare their numbers. Yeah, absolutely. Yeah. So without PowerPoint, it's just a sketch. Yes. Yes. So if you guys have this flex measure, another thing you could do, since this routine is saving also the Julian date, you should try to see how this uh, flux varies over time in the time period of 12 nights, consecutive nights. Um, that would be good. Yeah. And I think there are two chunks of that. Let me see here. Wait a second. So we have 22. There is another one here. Print. Okay. Oh, what's going on here? What? Oh, I think I lost the information. Wait a second. Let me do it again. Okay, so let me increase this here. Um, so we saw this one over here from 2 to 22 maybe. And then 848, 849. Oh, and then go down. How funny. 702, 703, 704, 4, 5, 7. There's another consecutive one here. Look at that. Is that the same one? It's it's funny. It's out of order. So let me see. One night, two, three, four, and then go to 2 nights later, 3 nights later, 4 nights later. So it's 4 and 4. I think this group here tried to get basically 2 rotational period consecutive. Yes, this is I'm printing here. I'm printing Julian date, so the whole array minus the first one. Correct, correct. Yeah. So yes, yes. So this is the Julian date that comes out of the FITS file. This is a big number. It has more, but it's truncated. This is what comes out, and we are plotting that. We are printing that minus the first one. Yeah. The Julian date. Oh, the Julian date. When I first read the FITS file, I extract and convert the FITS binary into safe binary in a file. And in that file, I put the Julian date because I knew we would need it just to see how variation would go in time. Yes, yes, yeah, it's already there. Not really, not really. Yeah, I don't have any routine here because Sylvia, I worked with her. She was the one who had all the routines, but it's not difficult to find, even in IDL. I think I can get that. But here, look at this. This is 19443, 444, and then it jump. Oh, 445. Yeah. Well, let me sort this data here. Just a second. How can I do that? Wait a second. Yeah, sort them, and then print a Julian date. Wait a second, you guys are in the middle here. Oh, wait a second. How do I take you guys out? Oh, there you go. Julian date, end Julian date, T trade Julian date, end 0 and 0. Okay. Oops. What? The first one? So print int. What is int? What? Oh, wait a second. I did it wrong. TJ day. Okay. Okay, that should be in order now. So 443, first night, second, two measures in the same night. Then the consecutive night had two measures, and then the next one another two. So 3, 4, and then jump, jump 4 nights. Probably was rainy. Oh yeah, I did. Oh yeah. Okay, let's start again. So 1, 2, 3, 4, 5, 6, 7, 8, 8, and then jump 2, né? 8, 9, 10, 11, 12. 12 nights. So 3 rotational period is 4 point. Yeah, that's what we thought. 4.2. So certainly somebody is trying to get something related to periodicity here. I wonder if whoever observed during these nights had anything published. Pretty sure, but you have to look that in the literature eventually. It was not me. Not really. Have to go back. I don't know if they released that information. I wonder. They, oh, the Fitz header? Um, okay. It doesn't give me anything here. Um, I have a. Yeah, I know. But wait a second. Like, how do I get that? I think it's MR. They do. Yeah. Yeah. Yes. Okay. Okay. How do I do that? When you say type, is type in terminal? Okay. Then I go. How do I? Okay. Which is here. How do I determine that? So this is um, um, too many things here. Okay, wait a second. CD dollars. capital like this, HOME, or HO home. Okay, all capital. LS. Oh, okay. CD TW. See how nice it is to be with the expert. Oh, TW. Yeah. And then LS, and then it's okay. It's right there, and that's the fit. So let's take one of these fits file, and then so copy all of these, right? And then type DS9. That's it. Lee, what did you do? Okay, I should be. Right here. Oh, I think this one. And then file, open. Okay, let's take the last one. Why is that? Hmm. Okay. Uh, go to spot and S for Sam. FV is not optimized for your Mac. Okay. Allow. Okay. Whatever. Open file. Oh, file. How do I? So I go to users. See Batalha. There. There. And then it's right there. Got that one. Open. Oh, skip messages. Oh, you did? Yeah. My turn now? Yeah. Cat. Oh, 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 okay. Oh, oh, is it get okay. Oh, it's an editor. Okay. Okay. Observer. Oh no. All of this for this. So we can. Well, this is a pipeline. This it could be that they are preserving the information. Maybe I don't know. The routine that I use when to get the mid observation. This number here above that, 2014. This one, yeah, yeah. And see if the guy has published anything since 2014. It's not that far. He- okay. Oh, that would be great. I was expecting somebody to say, "Oh, I can do that." No, no, they will be busy with flex determination. 2014, yes. So can we get something? Can we go at EASL and find it out now? Oh, let me take this away. Yeah, I don't know. We might be taking some time here. Yeah, probably science. We have to find Pharaohs first, or the 2.2 meter telescope. That's where it was. I wonder if there is a hourly glass somewhere here. Oh, search. 2.2 meters telescope. So it's being operation since. Telescopes and instruments. I would imagine it would have uh, the telescope would have a web page or so, right? No, that's not what I'm looking for. Yeah. Ferris data, 2014. I'll go. This is what we make use of it. Yeah. This is what we use to download and to find the data. Catalog 2, documentation. .2 meter telescope. Um, they don't have that, do you? Yeah, I don't know. Well, yeah. Oh, God. Science cycle. The principal foundations. Yeah. I don't know. When somebody has time. Yeah, yeah. 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 Yes. Where did you find it? Yeah. Reduce data query form. Process data. So here we set, we get shell 2.2 maybe. There you go. We got either. Then we search. Yeah, we already got that, but doesn't give the person. Oh, wait a second. Yeah. Oh, okay. Program ID is this one. So if let's go to the last one, 2014. Wow, 2018. I wonder. Oh, it's not available. So this is already available. Uh, oh, this one. Okay. Uh, okay. Let's go to the 214. 2000. 2014 was the last one. There is 2016 here. We have to download these new ones, but not now. Oh, a bunch. Oh my lord. 2017. Let's cut them. Okay. So you said this one here, right? Oh, there you go. PI name Patrick Wise. And what is this? This is this. Oh, description of the data. Okay. So Patrick Wise. Patrick. Is it like this? No. Boy. Okay. User search. Okay, wait a second. I have to go back. Patrick Wise. 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 Patrick Wise. TW Hydra. So he's interested in planets. No, no, wait a second. The evolving periods and the overall flicker noise characteristics of the Astro P8. So he published something in 2008. Rusinski, he works with Rusinski. Gunther, Dimitar. I know by name Gunther, works with planet stuff. Oh, let's beat them. Oh, look at this. The periodicity. Planetary explanation. Yeah, they are trying to get planet stuff. Certainly, they are not doing what we did or what we are trying to do now. Seven, yeah. Okay, so well, that's a good point. So let's say this coming week, I would take the paper that we work 2001, 2000, I don't remember when we published. And then for the following weeks, maybe one of us could get one of those papers based on what these people observe and trying to get the why they are interested in that data. And one of us kind of update and 30 minutes, 40 minutes of some of the important points they found, and then we go from there. There you go. There you go. So then you guys, you all should have access to the ESO portal, first of all. This is what I recommend. I mean, eventually we should, I mean, if we make I mean, you guys are all expert in AI, so you should find a way to take what we are doing in a scale of 92 files and escalate to different types of eShell format, and then get all the TW Hydra out there, and then do the same analysis using this outstanding Python language, and then get some outstanding result um, as complete as anybody can get. Um, there. Well, so there is a that's the old saying. If we are not the biggest and the most funded one group out there doing this type of things, we have to do some special thing. Yeah, I know. Other that's hidden. No one's caring for. All right. It probably was not part of on their expertise. Yeah. Accretion process. Yeah. Yeah. Well, because they are trying to see planets getting close to the star and causing some flickering in the accretion rate. The other thing I would like to see updated, because at that time we were not aware or too certain about it. I mean, TW Hydro has huge emission. So usually huge emission is associated uh, with accretion rate. So if you have a heavy accretion rate, you should be able to have the lines heavily veiled. And our lines are not heavily veiled at all. I mean, it has some 0.4, 0.5, 0.8, but less than 1. So the absorption lines are there. So which means it seems the star is at that time we suspect the star were tilted almost face on. And I would like some update on what's going on as far as new data is concerned on the inclination system of the star. So are we seeing the disk like this or edge on? So if you edge on, then it's complicated. If it's face on, if it's edge on is not complicated, it's good because we would see the spot coming in and out. But if it's edge on, would explain huge emission. It would explain low veiling and low rotation too, because this star rotates very, very little, 4.5 kilometers per second, which means the VCNI is would be almost nothing, right? So it's cosine of 190 degrees is 0. And that's why the lines are not broadened because of stellar rotation. But if that is true, if the spot is going around like that, we don't see a lot of variability in the spots. So veiling shouldn't show major variability. I don't know about line flux, basically. But as far as I remember, we saw a correlation between line flux and veiling. Um, all the time, yes. Um, okay, so the first part of what you said is true. I mean, we tend to associate the periodicity with spot migration that is being dragged by stellar rotation. Um, Now, accretion rate to be periodic, say it again? Yes, yes. So the spot can be triggered by two possible phenomena. One, the star itself has magnetic field and then create dark spots like the sunspots. So if the star has huge sunspots or dark or stellar spots, so as the star rotates, we see these spots going in and out of view, and they are associated maybe with the equator. I don't know, but you should see that thing going in and out. Now, if the spot's associated with accretion, which is also related to the magnetosphere of the star, then the spot is hot. It's a hot spot, and then we should see the migration of these spots occurring as the star rotates. If you are in some sort of a line of sight, so if you are seeing the star pull on, and if the accretion is all the way to the pole, and you are seeing the star pull on, the star can rotate as much as you can, and you won't see a lot of modulations there. So I'm curious to see if we will find any modulation in the line fluxes or in veiling, for instance. Yes, yes. We all see the spots, correct? Right, right. That's correct. But we wouldn't expect that to be periodical. I mean, I don't see how accretion rate can triggers any periodicity. I don't remember. In the paper, I think in the paper we suspect that was the case, was almost pull on, and I think Sylvia did some search and she found a paper of somebody suggests few degrees of inclination, which means you are almost seeing pull on. And then as far as I remember, I think she mentioned that, and I would believe she would put in the part of the paper she wrote. Yeah. I have to revisit that, so that's gonna be one of the topics that I will bring next week. Uh, I guess so. I think I save it. I pull up online and I save it. Let me see if I can find it. Yeah. Wait a second. I think it's blasted TV. Oh, there you go. Uh, Shoot, what happened? Last C22. Oh, there you go, Sylvia. Cannot open this file because the task is still inactive. Not correct. Okay. So you wanted me to get rid of this. Don't know why. Cancel. So I go here. Now I go to email. Oh, there you go. Flash roll. No, not this one. My computer is so slow. Something is going on here. Probably everybody in the house is watching Netflix. Okay, so no, why keep coming one treasure? I haven't even started yet. Okay, now here's the file. Now I will go here. Oh, I think I can. In fact, I can get from here, right? Yeah, Sylvia. There you go. And you computer savvy people might be dying with my inability to run this machine. Okay, I send it, so you guys might be receiving. Yeah. How come it didn't go? There you go. No, modulations that are periodical, especially over several, yeah, it's right here, over several, um, uh, some sufficiently large times. Oh, wait a second. Oh, she put it, the spectroscopy allows to infer the inclination of the stellar rotation. 18 degrees, between 0 and 15 degrees. So I don't know how she did that. This is the part that she did. Yeah, let me see. That's the decomposition she did. So the correlations are there. Error bar, you guys have to be aware of error bar. We have to have that well set. It's important. I thought I had done some periodicity analysis here. Yeah, 2.85 days. H beta veining corrected. Yeah, I think we settle in 4.2 days, which is the double or close to the double of this one. It's not exactly, yeah. 2.1 to 2.8. Yeah, I have to read it again, see what we did. I don't remember. This one? Yeah. 387. Yeah. This one? Yeah. Yeah, those diamonds are data for H beta. H beta. Yeah. And that is fitting the period in I don't know which, that's the phase. So that's the phase, but it doesn't say which period it is. Oh, that's the for 2.85. Oh, now I remember. We were kind of divided between two. One is 2.85, and the other one 4.51. Um, and that is the H beta with the 4.51. H beta. H beta. So this is H beta with 4.5, H beta with 2.85. And it's the second transition from the Balmer line to level n equal 2. Alpha is 3 to 2, beta is 4 to 2. It's about 4,800 angstroms. Yeah. Let me see here. Let's see if we have it in the data. I think we do. Yeah, is the equivalent. Yeah, is the flux is the flux divided by the continuum? But since the continuum is normalized to 1, so is basically the flux. Correct. No, the periodicity. She used a routine that use a Skardler prescription, and what it basically does, it takes your data points and then fold in different frequencies and see which one gives the minimum the minimum difference. Yeah, I think 4.5. Yeah, that's what we came out of it. You see it in the abstract. We should have put in the abstract. with no rotation on this and I. Yeah, this is okay. I still go with that. Observe over 2 years. We didn't put it. Why we didn't? We didn't have the balls. Should have put it. Yeah, it's not there. Yeah. Well, we were divided. I think somebody has put it periodicity in 2 days, and we see that, but we think that is an alias of the 4.5 or so, but didn't go in the abstract. We should have put in the abstract. I mean, this paper still receives some citation, so that's well. That's let's see what they find. Um, yeah, I mean, later on we should go and try to. Oh, look at this. Sodium line. Let me see if she has decomposition. To decompose. Yeah, let me see how that. Yeah, she fit. She tried to fit a Gaussian in the narrow component and another one in the broad component. You can see them here, right? Yeah. To decompose, yeah. But as you can see, I mean, it's unavoidable to see that there is a. Oh, wait a second. It could be this excess that we think is an excess to the red in as red wing in the narrow component. It could be some filling given by the broad component itself. Once you fit the broad component and subtract out, the remaining narrow component might lose its asymmetric characteristic. You know what? Because the broad component is all tilted to the red, as you can see here, right? And because this peak is peaking the red, it fills in the red wing of the narrow component. It could be the narrow component is symmetric. I don't know. You guys have another thing for you guys to certify. It seems that's the case here, according to what I'm seeing there. Right. Right. So let's say okay, the broad component comes from some turbulent region, right? Some pre-shock region or so. And then you say, okay, because of that, I will assume there is no movement in this turbulent region, or if there is a global motion. And then if that is the case, you fit a Gaussian and you find there is a global motion because it's red shifted. So that thing is falling as we see. So the broad component is peaking in the red, which means it's falling down towards the star. And it's turbulent because it's large, and it's falling the star because it's redshifted, right? And then we are happy with that. And then what we do after the fitting is to subtract out this broad component from the observing profile, and then what you have is what left. And then what you do, you fit a narrow component in in it, not a Gaussian in there. And then you say, okay, this Gaussian is formed by a different process. And then you have to explain what that process is. Well, I'm saying falling because it's red shifted. Yeah, you're right, right. especially especially if we are seeing the system incline almost face on. Yeah. Yes. Well, ideally, if we are so confident about the veiling, we measure, right? So you guys are certain that what we are doing is the best. Then, if you also can decompose this profile in two components, right? Let's say you can do that. Then, does the veiling we measure over these 92 data sets correlates with the narrow component? How correlated it is? Does it correlate with the broader component? How correlated it is? And then you can discuss effects. Helium, this helium line is not only excited by collision, so you need to have a hot gas dense that collision can be efficiently to create all this crazy emission, but helium can also be excited by radiation. So if you have a UV flux or a strong ultraviolet radiation with all these hot spots, certainly you can have that. So helium can be this UV radiation can excite the helium, ionize the helium, and by cascading down, it can create this emission. So we have two possibilities of exciting helium. One is radiation, and the other one is collision. So in any case, it seems that, and that I would like to see it, if this narrow component is that centered in 5875.621. If that is the case, it's not moving with the star. It's pretty much at rest frame with respect to the star. So yes, yes, which means yeah, the narrow component is is kind of a root to the star. It's not formed by the star itself because the star doesn't have enough energy to create this emission, but has to be related to, in fact, that has to be determined, but I would expect this emission is associated with the accretion somehow. But it is rooted to the star, is not falling if if it is dead centered in 5875.621. That means whatever region is creating this emission is anchored in the star itself. So the star rotates, that thing goes along with the star, and that's why is centered at rest. Yeah, or it could be formed in a hot spot because you have hot gas and you have dense regions. Yeah. Yes. No. It does. It does. There are stars. I forgot V410. I think V410 Tau. I think that's what it is. Is one of these T-Tauri that has gigantic, supposedly gigantic dark spots. Yeah, but all triggered by magnetic fields, basically. Oh, some dog is trying to participate there. All right. Okay, so I will send a survey to see when we can get together next week, and then we go from there. The dog approves. That's settled. All right. Okay. So and Shaunak, email me if you. I will. Oh, let me send the files now before I forget. Let me save this routine so just to make sure they are the latest one. How do I do that? I think I close save the file. Save as. Flux file. Save as. Save. Yes. And then send to you all. Hmm. Okay, so you need pro. Oh, there you go. You need this. You need this. And you need this. Because I put another call. There you go. Yeah, so and basically the only thing you need to do is to change the address inside the routine. Okay? Good enough? All right. I'm gonna go burn some fat now. Okay. Sounds good. Sounds good. Okay, Vikas. You too. Okay. Bye bye. Bye.